Okay, so this is 15.3 and probably 15.4, depending on how long 15.3 goes. Okay, so you'll notice we're skipping 15.2. That's limits and continuity. If you're a math major, you'll probably want to learn that stuff, but you probably will in the future in an analysis class. Otherwise, I think it's probably a good idea to skip it because most people in this class aren't really going to need it. And especially since it's a summer class, I think it's better just to skip it and just jump right into working with derivatives, which is this section, by the way, so partial derivatives. All right, so again, if you are a math major or perhaps a physics major as well, maybe you take a look at 15.2. It goes through kind of the background, the foundation of the definition of the derivatives, these partial derivatives that we're going to be talking about, and also the idea of continuity in the multivariable setting. But again, for us, I think we can afford to skip it. Okay. So in one variable calculus, you have a one variable function and with the variable x, and you can take df dx, right? And what that represents is how the function changes, right, at this particular point. It tells you how the function is changing at that point, right? So I guess in this particular example I've drawn, df dx is, df dx, df dt will come later, but df dx, our function is decreasing at this particular point. Okay, so now we're going to have multivariables, and for most of today, I'm just going to concentrate on two variables, f of x comma y, but the extension to 3 variables and 4 variables and whatever number of variables is very, very straightforward. Okay, so for multivariables, you've got 2 variables instead. So perhaps a natural thing to look at is, well, first of all, df dx is how your function changes, right? F changes, how the output of your function changes relative to your inputs, right? Relative to how x is changing, right? So df dx is, just in words, right? If you move in the positive x direction, right? How is your function? How are your outputs changing in terms of the picture in the y direction? Okay, so now we can kind of think about, well, how does my outputs change depending on how my inputs change, either my input x or my input y. Okay, so now we have 2 possible inputs. So there's 2, at least in our first kind of attempt at thinking about derivatives, there's two variables, so there's 2 kind of derivatives to think about. Okay, so one is kind of in the x direction, and the other one is in the y direction. Okay, and so that's exactly what gives us partial derivatives. So we use the word partial because there's essentially 2 derivatives. Again, each one kind of representing each of the 2 variables, and so each one gives you kind of like a partial bit of information, I suppose. Okay, so how do we compute these? What do they mean? Let's get into that. Okay, so let's start with a picture just in the domain of my function. So again, I'm talking about a 2 variable function. So the domain is in the plane, x and y. Let's say we're interested in this point right there, how my function behaves at this point. Let me call that point a comma b. All right, so x equals a, y equals b. All right, so that would be this. This picture would be analogous to a picture in the 1 variable case where I just drew the line, right? That's the domain. And then I noted that point right there, x equals, let's call that x equals a as well. All right. Okay, so there is no, so right now it's just my picture down here is just the equivalent to that picture right there in the blue box. Okay, there is no graph of the function yet. Okay, So we're interested in what's happening at AB. Like we said, it looks like we have two variables or two unknown quantities. And so we can try to think about, well, what happens as x changes as we move away from this point of interest, right? So when x, right, so at this point, x is equal to a. So what happens when x gets bigger and bigger and bigger away from a, right? So just x. So y, let's say for now, is just constant, all right? So y is just staying at b. So in other words, we're looking along this, this line segment right there, right? So we're trying to figure out how the function changes as we move along this horizontal line segment, okay? So how the function changes as we move along that horizontal line segment, again, keeping y at the constant height of b, right? X is changing. That's going to be what we call the partial derivative of f with respect to x, okay? All right, so what exactly is this partial derivative? Well, actually, I basically just described it. So if you think about it the way I just described it, where we're moving along this line and x is changing, right? X is a variable that's changing. Y is fixed at b. Y is not changing because we're on this horizontal line. So the height of my, my coordinates is always b. So then what we can see is we have actually a one variable function, right? Because what we're looking at, right, if we look at the values of f as we travel along this line, right, the values that we're going to be plugging in are going to be f of something, right? Like we said, x is changing, comma, but y is always b, f of something, comma, b. All right. Let's be a little bit more precise. And that something, of course, is x. Okay, so this is one variable calculus now. Okay, because our function now depends only on one variable, right? And so one variable calculus, we're all comfortable with that. We know how to take derivatives with one variable calculus. So we can just take the derivative of this, okay? And that exactly is the partial derivative of f with respect to x, all right? So our notation with partial derivatives is df dx with curly d's. So whenever we talk about derivatives of multivariable functions, we use curly d's as opposed to straight d's, as you'll see up here with in one variable calculus. All right. So if your function depends on one variable, we use the straight d's. If your function depends on multiple variables, then we use the curly d's. All right. Okay, so df dx is, this is at the point of interest, and we're looking at the point a comma b, all right, is equal to just a regular derivative df dx, so I'm going to use the straight d's for now, of this function x comma b. Maybe I should write it, let me write it like this. So df dx, I wanted to write d dx of f of x comma b. All right, so again, this is a one variable function. And so this is one variable calculus. Okay. And so what we've done is we've reduced kind of the question of, what is the partial derivative into a question of just computing something in one variable calculus. Okay. And this is this derivative d dx, of course, is computed at x equals a, right? Because that's our point of interest, right? We're calculating right there. Okay. All right. Let me fix that d dx right there. Okay. Before we do any pictures, before we do any computations, let me show you a picture of what's going on. Let me draw a three-dimensional picture, x, y, z. So let's say our point of interest is right there, a comma b, right? So here is a, and there's b. So what are we doing? We're looking at essentially values of f as we travel along this line right there, again, parallel to the x-axis, y is constant, right? So if we have the graph of our function, perhaps, let's say, looks like that, right, above above the xy plane, then let me kind of cut the graph with this line extended upwards, and it'll look kind of like a curved thing, right? Something like that. Okay, let me exaggerate it to make it more curved. Just to emphasize that this thing up here is actually perhaps a complicated function. All right, and so what we're doing essentially when we do this computation up here with this df partial f partial x is we're looking at the one variable calculus function where x is, well, where the variable travels in this direction and our outputs are exactly that guy there. So you can see if I look in this plane right there, I'm doing one variable calculus. All right, inputs down here, outputs up here, inputs down here, outputs up there. That up there is a curve, right? Which is exactly what you have when you have a one variable function, right? So something like that, right? So we're essentially doing something like that. Okay. All right, so literally one variable calculus. Okay, so it's exactly telling you this partial derivative is exactly telling you how the function is changing in the x direction as x changes. Okay. All right. So given that we're not changing y at all when we do this this partial derivative, that means it's really, really easy to take partial derivatives. So for example, let's say f of x comma y is equal to x cosine y plus x squared plus y cubed, something like that. All right, so a pretty complicated function. What is partial f partial x, or df dx? At any point, right, we're just going to calculate it in general. Well, we think of it as above, right? When we calculate the partial derivatives, we're thinking of the y coordinate as just a fixed number, right, b. And so here, down here, we're just thinking of y as a fixed number, right, perhaps b, okay, or whatever point of interest we want to look at. So when we take our partial derivative, when we actually do computations, we don't always have to kind of substitute in a b and then do the computations, right? We can just think of y as a constant and take the derivative of this right-hand side here, just thinking of y as a constant. Treat y as a constant. Okay, so x is your only only variable. And so if y was a constant, this cosine y is just a constant. That y cube is just a constant. So when I take the derivative, I'm just going to be essentially taking the derivative of cosine y, which is a constant, times x, and the derivative of that would be just cosine y, right? Plus the derivative of x squared, which is just 2x, plus the derivative of y cubed, and again, y is a constant, so plus 0. Okay? And so that's it. df dx is cosine y plus 2x. Okay? And again, the interpretation of this, for example, df dx at, let's say, 1 comma 2 would be cosine of 2 plus 2. What does this number, what does it mean? It tells you how your function is changing as you move in the x direction. So here's 1 comma 2, right? Not to scale, I guess. As you move in the x direction, how does your function change? Does it increase? Does it decrease? That's exactly what this number tells me. Okay, but again, it's very important to emphasize this only tells me what's happening in this one single direction, the x direction. Okay. All right. Now we have f depending on x. We also have f depending on y. What is df dy? Well, same idea. Okay, so if we were looking at our point a comma b like above, a comma b, instead of looking at how our function changes as we move left and right, we're thinking now about how our function changes as we move up and down in the y direction. Okay, and in this situation, you can see if I only look along this red line here, a is constant. Okay, so how f changes does not depend on the first variable at all. right? And so exactly literally the same idea, when we calculate df dy of whatever function, we just treat the x as a constant. So I guess our function up there was x cos y plus, let me do the same example, f of x y equals x cos y plus x squared plus y cubed. Okay, so when we take the derivative in the y direction, when we think about how f changes in the y direction, x is constant. And so df dy would be, well, x is constant, so we just leave it out in front. Derivative of cosine is minus sine, so minus sine y, plus x squared. X is a constant, so the derivative of a constant is 0, right? So 0 plus, and then y is our variable, so when we differentiate y cubed, we get 3y squared. Okay, so once you get used to this, it's super, super straightforward. Just, think of whatever you're differentiating with respect to, all your other variables, if there's 1, if there's 2, if there's 3, no matter how many, all your other variables are to be thought of as constants. Okay, so minus x sine y, sorry, that's a little messy there, x sine y plus 3y squared. Okay. And so df dy, for example, at the same point 1 comma 2 would be equal to minus 1 times sine of 2 plus 3 times 2 squared. And that would be minus sine of 2 plus 12. Okay. And again, you get the same kind of interpretations as from one variable calculus, because this is literally one variable calculus, right? So for example, I noticed that this right-hand side right here is a positive number because sine can never be bigger than or less than minus, can never be bigger than 1. And so when I add 12, right, this guy here is for sure positive. And so that means df dy at 1 comma 2 is positive. So that means as my function, as I move my in the y direction from 1 comma 2, again, as I move in a positive y direction, I have to emphasize that, from 1 comma 2, my function is increasing. All right, so the graph of my function, let's say again, this is x, y, z. Here's 1, here's 2. Oops. Let me put 2 over there. Right? As I move in a y direction, my function above this is going to be increasing. So perhaps it looks something like that, right? Increasing. Okay. Let me draw it like that. Okay. So same interpretations, but again, just like with df dx, this only tells me how my function is changing in the y direction. All right. Okay, that's actually going to be a big problem for us that we'll resolve by the end of this, midway through this lecture. But again, it's really important to emphasize, right? For now, df dx only tells me how f changes in the x direction, and df dy only tells me how f changes in the y direction. So a natural question would be, how does f change as I move, in one of these kind of in-between directions, right? So in this direction, it would be, the information would be given by df dx. The information here would be given by df dy. But what about all the other directions? Okay. All right, we'll address that very relatively soon. But before we do that, let's talk about, this was two variables. Let's talk about what happens if you have 3 variables or more. Then in this case, you would have df dx, df dy, df dz. All right. So it's literally the same idea. Df dx is how f changes as you move in the x direction only, where y and z are fixed, are constants. Okay, so I guess in terms of a picture, here's your domain, x, y, z, right? Because now we're in 3 variables, so your domain has to be 3 variables. If we're at the point, for example, 1, 2, 3, right? So let's say right there, 1, 2, 3. Right? df dx would be telling us how our function changes as we move in this direction. All right? Only. So again, as we move along this line right there, right, you can see our y is fixed and our z is fixed. Sorry, I probably should have drawn that up where my point was, my point of interest, right? So let me draw it up here, right there. All right. So z is fixed. It's this line that I've drawn is completely constant at a height 3, at a constant height of 3, right? Its y value is constant at 2. Only the x is changing. And so again, when you calculate df dx, just treat all your y's and z's as constants. If you calculate df dy, just treat all your x and z's as constants. For df dz, treat your x and y's as constants. Right? So again, the basic principle is whatever you're taking your derivative of, all your other variables are to be thought of as constants. Okay? And of course, we can extend this to no matter how many variables we want, x1, x2, x3, whatever, x100, right? Then df dx27, that's going to be how my function changes in the direction of x27, right? With all the other variables considered constant. Okay, so just one more quick example. If I had fxyz equals, for example, 2xyz squared plus xy plus yz, right? Then df dz would be equal to, well, 2xy, that's just a constant, so 2xy. Z squared, derivative of that is 2z. Plus x times y, well, x and y are constants when we're doing df dz, so plus 0. And then plus, again, y is a constant, so just y times the derivative of z with respect to z, which is just 1. Okay, so this is just going to be 4xyz plus y. All right. Okay, of course, it turns out to be still a 3-variable function, right? Okay, so computationally, these partial derivatives are very, very straightforward. But we're gonna, our next thing, right after we talk about one small thing, is gonna be how to talk about derivatives in other directions, okay? All right, but the one small thing we want to talk about is just notation. So if we have, again, let me just do the 2-variable situation, f of x comma y. I already said we can do df dx, df dy, right? So this is kind of like the Leibniz notation of, this is equivalent to kind of df dx for a 1-variable function. Let me not use x, let me use t for a 1-variable function. So if I had f of t on the 1-variable calculus side, all right? But of course we know in 1-variable calculus we can talk about f prime, right? Well, for 2-variable, as an alternate notation, we can't use f prime because we always need to know, right? Are we taking the derivative, partial derivative, with respect to x or y? Which variable, right? Are we considering changing, right? So the equivalent notation for multivariable calculus is f sub x and f sub y. Okay, so that's literally the same as df dx and df dy, just purely notation. Okay. Let's see. Of course, if you want to plug in a value, so this would be, if I wrote f of t, f prime of t here, I guess I should write kind of a similar notation here, fxy, fxy. Okay. If you're plugging in values, you can use the same notation, this evaluated at t equals 1, right? This was what you would have done in 1-variable calculus. And here you evaluate this at whatever, 1 comma 2, right? Evaluate this at 1 comma 2. So this is the notation the book uses. An alternate notation for df partial f partial x evaluated at 1 comma 2 would be like this, ddx at 1 comma 2 of f. That's literally the same thing, all right? Just a notational difference. Okay, I actually like this second notation better because if you take more math, you'll see that this ddx and this ddy actually represent mathematical objects. And so when you write this, you're saying take this mathematical object and apply it to f. All right, small thing, don't even worry about it. But But you may notice me writing, doing all sorts of variations of these notations. Okay, so having this notation, one thing you might think about is, what about f prime prime of t, right? What about that in multivariable calculus? Well, you can certainly take more derivatives, and the way you do that is the same idea as in one variable calculus. So what is f prime prime of t? It's just the derivative of f prime of t, right? If I take the f prime of t, and then I take the derivative of that, that's literally the definition of the second derivative, okay? Maybe that's a little more clear. So what about in multivariable calculus? Same idea, right? You can have df dx, and then you can say, well, df dx is a function. What happens if I want to know how this function changes in the x direction, right? So that would be, the second derivative would be something like dx of df dx, okay? All right, the notation for this, because we don't always want to write, all these d's unnecessarily, is d squared f dx squared, okay? So this would be taking the derivative of f in x direction, right? The result of that is a function, and then we can take the derivative of that in x direction again. That's d squared f dx, dx squared, okay? All right, why, one thing you might be wondering at this moment is why there's a 2 here and a 2 there. Seems kind of unnecessary. Well, the reality is that there's actually more partial derivatives, right? If I, again, look at df dx, I can wonder how that guy changes not in the x direction, but in the y direction. So that would be d dy of df dx. Okay, so the way we would write that is so perfectly legitimate again. So the way we would write that is d squared f dy dx. Okay, so the square up here tells us I'm taking 2 derivatives, and then down here I'm writing down exactly which 2 derivatives. Okay, again, the square is kind of unnecessary because you can just count the number of d's down here, but it's a nice nice way to instantly see how many derivatives you're taking of f, right? So that 2 tells me in total I'm taking 2 derivatives of f. One in this particular situation, one with respect to x and the other with respect to y. Okay, now of course we have df dy, and we can take derivatives of that with respect to y, right? So that would be d squared f dy squared. And then the last possibility is df dy, and then you take the x derivative with respect to that. So that's d squared f dx dy. Okay. All right, so in total, there's actually four partial derivatives, 4 partial second derivatives. Okay, so immediately you can see that multivariable calculus is going to be more complicated because, right, here we have 4 partial derivatives in one variable calculus. We just wrote f prime prime, right? Okay, in fact, 4 partial derivatives isn't even the right way to think of it. The correct way, which we're not going to go into too much, certainly not right now, is the second partial derivative should be thought of as a matrix of 4 elements, where each of these guys goes into one of the elements. So it's even perhaps more complicated than it appears. Okay, but the matrix representation, or the way of the thinking of second derivatives of matrices, we'll touch on a little bit when we talk about the second derivative test in the near future. Okay, I think next week even. All right, let's see. Oh, notation. So this is the Leibniz notation, the partial notation. Of course, the equivalent of these would be fxx, fyx, fyy, fxy. All right. Okay. Now, ordering. So here we have two interesting things going on, or one interesting thing going on. We have dy ddy of df dx, and we have ddx of df dy, right? So we have this ordering that appears like it matters, right? Whether I take the derivative with respect to y first or x and x second, or x first and y second. And same idea here. It appears like we might have these two guys down here be different. Okay, but as far as our class is concerned, for pretty much all the functions that we're going to be looking at, fxy is equal to fyx. All right, so let me write this as mostly. Okay, I'm not going to go into it too much, but this is pretty much true for most of the functions we're going to play with. I'm not going to trick you on an exam or anything like that where I give you a function where this doesn't work. Okay, probably for most of you in your math careers, you're never actually going to work with functions where this is not true. Unless it's obvious, right? Unless you literally have a function that's not, doesn't have derivatives or something like that. So I'm just going to leave it at that, right? If you do look in the book, in this section, they'll give you a criterion for when this actually is always true, and it's a pretty, it's very unrestrictive. Basically, when is this true? Well, if you're at a point where in a small neighborhood of that point, so this is let's say this is my domain of my function, and I'm interested in the point a comma b. All right, so I want to know at a comma b is f sub xy equal to f sub yx, right? So basically, if you can find a small neighborhood of this this point where both of these functions are continuous, then you're all set. All right. So if you look at the functions that we often work with in this class, that criterion is satisfied. So we're not going to worry about it too much. Okay. So for example, all the examples functions that I've given, it's true. So if I take the second derivatives of this guy, second derivative of this guy up here, x cos y plus x squared plus y cubed, their second derivatives are all going to be continuous. And so there's no worry. fxy is going to be equal to fyx. All right. Okay. But perhaps, just file it in the back of your head that in real life, there might be situations where this is not true, especially if you're a math major. That's something that you actually do. You actually might have to worry about in the future. Okay. Let me actually do an example just to confirm that this actually works, right? So fxy equals, let's say, x squared minus natural log of x times y squared. Okay. So f sub x is equal to 2x minus y squared over x. F sub xy, or f sub, let me do it with the other notation, because it's more, the other notation perhaps I think is more clear which one you're doing, which derivative you're doing first, which derivative you're doing second. So let me write it like this. Equals the derivative of this guy above with respect to y. And so this 2x goes away because it's just a constant, minus the derivative of y squared is 2y, so 2y, and then the x is just a constant. Okay. All right, if we do it the other way, f sub y first, we're going to get the x squared is a constant, it goes away. The natural log x is a constant, so we just have a natural log x in front. The derivative of y squared is 2y. Okay, and then so df dy, and then df ddx of that is going to be the x derivative of this guy above. And that's just going to be, well, the 2y is constant, so minus 2y, and times the derivative of natural log is 1 over x. Okay, and so of course, these two guys are the same. All right. Okay. Everything I talked about here, works for three variables as well, right? So if you have f of x, y, z, then you're going to have a whole bunch of partial derivatives, right? F sub x, x, f sub x, y, f sub x, z, f sub y, x, f sub y, y, f sub y, z. F sub zx, f sub zy, f sub z, z. Okay. All right. So again, this whole study here of multivariable calculus is going to be more complicated than in one variable calculus. And in fact, you can actually we said something about the correct way of thinking of second derivatives is as a matrix. Well, the matrix would be something like this. All right. And again, for our class, the functions we're going to be looking at, unless it's completely obvious, there's a problem. For example, what I mean by that is, this when you're dividing by x here, you certainly can't work with x equals 0, right? Okay, so pretty much for the purposes of our class, right, this matrix is actually really nice, right? xz, zx, those two are the same. yz, zy, those are the same. xy, yx, those are the same. So this is actually a symmetric matrix if you've taken linear algebra. And those are, symmetric matrices are really, really powerful tools. Okay, again, we'll talk about this matrix idea when we get to the second derivative test. Okay, and of course, certainly you can take more derivatives. You can take 3 derivatives, 4 derivatives, however many you want, right? You can take f, x, 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 however many times you like, right? Again, perhaps the other notation would be better in this case. 1, 2, 3, 4, 5, 6, d6f, dx6, okay? All right, by the way, now that we know the order doesn't matter, right? So f, x, x, y, y, x, we can just write that as d 1, 2, 3, 4, 5, d5f, and then dx cubed dy squared. All right. So we don't actually have to write the order because, again, for the purposes of our class, it doesn't matter. Okay. Let's now address the big problem. So let's go back to 2 variables, x and y. This is the domain of our function again. I'm looking at, let's say, the point AB, right? I now understand exactly how my function changes as I move in this direction, partial f, partial x, right? I now understand perfectly how my function changes as I move in that direction. That's partial f, partial y, right? But what happens in these other in-between directions, right? All these other directions, how does my function change? Okay, so that's the question. And we certainly want to know this, right? Because we can't, in real life, be just lucky enough to only have to know how our function changes in these particular special 2 directions. Okay, so how do we talk about that? Well, the bad news is, at least just without any special conditions on f, we're just in trouble. Because ideally what we would like, because we have a function of 2 variables, x and y, we would like the partial f, partial x, and partial f, partial y to give us all the information we need about the derivatives in the other directions, right? But that just simply, if you think about it, it just can't work. For example, I can easily make up a function, x, y, z. I'm just going to kind of do a graph. Here's a comma b, my point of interest, right? I can easily make up a function where f is constant here. Let's say just constant value 0 there, right? And constant value 0 here, okay? And so df dx, I guess I should give these names a and b, at ab, right, is just 0 because f is just a constant, right? df dy at ab is equal to 0 as well, okay? Because again, my function is just constant here, okay, with the value 0. So let me write f of x y equals 0, f of x y equals 0, on these two lines. Okay. However, I can easily make up a function. I can fill in this in-between part, right, so that the function actually is not, the derivative is not 0 in between, right? So maybe it's curving upwards or something like that. All right. So what that tells me is that knowing df dx and knowing df dy cannot tell me about how my function changes in the other directions, because these two are 0, 0 and 0, right? How are you going to get another number, right? For example, how my function changes in that direction. How are you going to get that from the 0 here and the 0 there, right? It doesn't seem possible. And the bad news is it's not possible in general. All right. So the in general is the good news. So what I mean by that is that for the functions that generally we want to study, and certainly for the functions that we play with in our class, df dx and df dy are going to be able to tell us everything we need about how our function changes in the other directions. Okay. So again, in the most general situation where I know nothing about f, df dx and df dy are not enough to tell me about how my function changes in other directions. But because we're lucky, most real-life problems, let me put it that way, involve functions which are special enough that df dx and df dy are actually enough. All right, and those are the functions we're going to restrict ourselves to in this class. All right, so very similar to the situation where I just talked about fxy being equal to fyx. We're just going to consider functions basically where that's true. We're only going to study functions in multivariable calculus where df dx and df dy tell me everything about my function. Okay, so so notice, because of what I just said, in one variable calculus, so if I have just f of t, right? If I have f prime of t, then we say differentiable. Right? If f prime of t exists, then we just say the function is differentiable. But now in two variable calculus, if f df dx and df dy exist, we can't necessarily say the word differentiable. All right? Differentiable is actually reserved for functions where not just df dx and df dy exist, but it's reserved for functions where df dx and df dy exist, and df dx and df dy can tell me everything about how my function changes in all other directions. Okay. Okay, so let's talk about what kind of functions those are. And again, the good news is it's basically most functions. So for example, if you look at all the examples I've given, those are going to be differentiable functions, except at at places where it's obviously not differentiable, like where you divide by x or something like that. Okay. All right. So in order to talk about this concept of differentiability, or what should be the concept of differentiability in multivariable calculus, again, just saying df dx and df dy exist is not good enough. All right. So in order to talk about this concept, let's go back to one variable calculus and think about what the derivative, what's the meaning of the derivative? What's the essence of the derivative? So let's say we have a function f of t. Let's say we're interested in the point t equals a. All right. One thing that we did in one variable calculus was we studied linear approximation. Right? And the idea was that if the graph of your function looks like this, and here's t equals a, if you draw this tangent line right there, right, whose slope is f prime f prime at a, then my function f of t near a is roughly, well, it's roughly the linear approximation. So f prime at a times x minus a plus f of a, right? And again, this is the equation of that line. Of this line. Okay, so this is actually the essence of the derivative. The derivative of a function essentially allows me to treat my function as a line. All right. Of course, again, there's a lot of caveats here, right? You have to be near A, right? How near A? Well, that depends on, if you want to do more analysis, it depends on the second derivative, right? That tells you how accurate this approximation is. But the general idea is that the derivative, having a derivative basically means that you can approximate your function with a line, all right? So that's the idea that ports over to multivariable calculus. So being differentiable is not that df dx and df dy exist. Rather, being differentiable means differentiable in multivariable calculus means f of x comma, again, I'm just going to restrict myself to two variable functions for now, means f of x comma y is approximately something like this in terms of, the analogous thing, the thing that's analogous to the line, the tangent line, right? So thing analogous to tangent line. All right. Okay, so again, to be differentiable in multivariable calculus is going to mean that you can approximate f with this analogous thing. All right, and this analogous thing, of course, is going to involve partial derivatives. All right, so the first question is, what is this analogous thing? Well, in one variable calculus, we approximated f using the tangent line, right? So now, because functions, the graph of a function is a surface, we're going to approximate functions with a tangent plane. Okay, so this is going to be a tangent plane. Okay. All right, so what I'm going to do next is I'm going to try to figure out what this plane should be, and we'll move from there. Okay, so the point of view we're going to take right now is if this tangent plane exists, then what should its formula be? All right. Okay. So let me actually use this picture up here. So let's say here's our point of interest. We're going to want to figure out the equation of this plane. All right. So this is the graph of f of x. Right. We're going to use actually our knowledge about how to find the equation of a plane. Right. So let's say we're interested. So this is x and y and z. Let's say we're interested in the point a comma b. So that would be a, and this would be b. And so that means that this height up here, because it's on the graph of my function, right? That height right there is going to be f of ab, right? So the coordinates of that point right there is going to be a comma b comma f of ab. All right? We're going to need that because we want to find the equation of this plane. And so how do we get the equation of a plane? We need a point and we need a normal direction. Okay? So this guy right here is going to be my point. All right. So all we have to do now in order to write down the equation of what should be the tangent plane is to figure out the normal direction. Okay. How do we find out the normal direction? Well, we're going to take the point of view that if we find two vectors that are in the plane, then we automatically get the normal direction by crossing those two vectors. Okay, so we're going to find two vectors that are along this plane. So let me draw the picture again. It's getting a little messy up there. So I got A here, I got B here. Here's my point of interest. Let me draw the function over here. Above, I've got this plane, right? It's not flat, so it could be tilted. Let me kind of emphasize that. All right, so how do I find vectors along this plane? Well, one thing I can do is I can say, if I travel along, so this is, sorry, let me label these, x, y, z. if I travel along the x direction, right, up here, again, I'm going to get a curve, right, just above this line segment there. I'm going to get a curve passing through that point. Okay, AB comma f of a comma b. All right. If I figure out the tangent direction of this curve, let me use blue. All right, let me say something like that. Right, that's going to be on the plane. Okay. In the same way, if I look in the y direction, right, above, I'm going to get a curve, a different curve. It's going to look like that. The tangent to that curve is also going to be on the plane. Okay. I kind of regret doing this all in the same picture. Maybe something like that. Okay. So I've got two curves, right? One corresponding to when x changes, the other corresponding to when y changes, right? That gives me two curves up here. And we can just find the tangent direction of those curves. And if I cross them, I'm going to get the normal direction that I want. All right. I combine that with my point, and I've got the equation of the plane. And that's going to be what's supposed to be my tangent plane. All right. Okay, so let's actually do this. Let me do it just kind of in a one variable calculus way. So I'm going to, let's look in first the x direction as x changes. So I'm going to be looking in, sorry, there we go. Okay, I'm going to be looking in this plane right there. All right, and it's going to cut my graph kind of like that. All right, so the plane that's at y equals b. All right, so this is the plane y equals b. Okay, so the reason I'm doing this is so that in essence, I just have a one variable calculus problem, right? So I have z and I have x, and then I'm not even going to bother to draw y, right? We're at y equals b. Okay, so my function above is going to look, like I said, like that. I'm at x equals a, and I essentially want to figure out this direction right there. Okay. All right, what is that direction? Well, this curve right there is the part of the graph of f of x, comma y, right? And so this curve is going to be given to me by partial f, partial x. Because partial f, partial x is literally, it literally describes how my function changes as I move in this direction, as I move in a positive x direction away from a. All right? So the slope of this arrow right there is partial f, partial x at a comma b. Right? Again, we're fixing ourselves at y equals b. Okay? All right. So what would be a direction for this line? Well, one way to kind of look at it is the derivative is like the slope, right? So if I move one step in the x direction, then I should be moving one step vertically by the amount df dz. Okay? And again, this is all happening at the point a comma b. All right? Okay, so that means my vector that comes from looking just in the x direction, this vector, oh no. This vector right up there that's on my tangent plane is going to be the vector, so let me call it v1. That's going to be the vector I, right? Because one step in the x direction, plus 0j, because we're not moving in the, this arrow is not moving in the y direction, right? Because we're on this yellow plane where y is just a constant. And then plus df dz at a comma b, k. All right. Okay, notice this is just a constant vector, right? 1 times I, 0 times j, df dz at ab, which is just a number, times k. Okay. I guess the way I've drawn this picture, df dz is a negative number, which is not a problem. Okay, So this guy here is a vector that's on my plane, right? On the plane that we're trying to figure out the formula for. Okay, now we can do exactly the same thing. We can take a kind of a planar cut of our whole picture in the where x is a constant, right? So let me see if we can do this. So we can do a planar cut in this direction, right? And then what we would see is a situation where we just have the variables y and z, where x is just a constant, x equals a, right? Here we're interested in the point y equals at b. The graph of our function would look perhaps something. Let me kind of exaggerate it, make it look different. So let's say the graph of our function looks like this, right? That is the direction that we're looking for. But again, how that the slope of that direction is literally df dy at a comma b. Okay, and so this is slope of this guy right there. And so again, if you want to convert that into a vector direction, what does this df dy mean? It means if you move one step in the y direction, you should move up in the z direction, df dy at ab. Okay, and so my second vector should be 0i, because we're not in the x direction at all, plus, plus j, right? One step in the y direction means we move up or down, whichever is appropriate, a comma b, depending on the sign of this term right here, times k. Okay. So this is on the plane. All right. By the way, we're talking about this now. This entire discussion here will help us next week when we talk about linear approximation. So it might seem like ultimately at the very, very end of this, it might seem like you don't care about this, but because ultimately we're going to have some really nice formulas pop out at the end. So it seems like going through all this is a waste of time, but actually going through all this will help us discuss linear approximation next week. All right. Okay, so we've got our two vectors on the plane, right? So our picture might be something, I'm just gonna draw the plane. So our picture might be something like, this is our v1, this is our v2, right? And our point is, again, a comma b comma f at ab, all right? And so the tangent plane, the equation of what should be the tangent plane is going to come from taking the cross product of v1 and v2. That gives me my normal. So let me actually just do that, ijk. All right, let me do it in the kind of determinant method. 1, 0, df dx. And again, this is at ab, but I'm just going to drop it because it's going to get really messy. So I'm just going to write df dx and df dy. Okay. Again, technically, I should do it. AB, AB. Okay, I regret it. It's a little too messy, so let me get rid of all that. Okay, so we'll just remember, this is all at the point AB, so all of these are numbers. So there's nothing, crazy going on here. Okay, so what is this? This is going to be I times minus df dx at AB minus j times df dy, and then plus k times 1. All right. So ultimately, this is minus df dx, I, minus df dy, j, plus k. So that vector is normal to my plane. All right. So this is my n. And so we have our point. We had our point was was AB, f of AB, right? So the equation of the plane, the equation of what should be the tangent plane is, we're just going to purely quote the formula now, right? So minus df dx, and here I'm going to emphasize the AB here, to emphasize that this guy is just a number, all right? x minus a. So the x here is a variable, the a is a constant, the thing in front here is a constant, minus df dy at ab, this is a constant, right? If we're interested in the point a comma b. This is y minus b, right? My point is at b. And then finally plus 1, right? Because 1 times k. And then z minus f of ab equals 0. So I guess let me put the equal 0 on this side. Okay, so this is the equation of my tangent plane. All right, so this is my tangent plane. Or this is what should be my tangent plane. All right, I guess I should say it like this. If there was a tangent plane, this is what it should be. Okay, so again, I'm being somewhat vague here because again, we're not doing this very, very carefully mathematically with limits and all that. In fact, if you look at the definition, the technical definition of differentiability in the book, there'll be delta x's, delta y's, epsilons, and stuff like that. You can get very technical with it, and you should if you're a math major, but I'm going to keep it less mathematical and maybe more intuitive. All right. Okay, so there is quite a bit of vagueness here. So when I say something like this is what should be the tangent plane, it's not completely clear what that means, right? Okay, but this is what should be the tangent plane. If there was to be a tangent plane, right, this should be its formula. All right. Okay. So remember we started this actually with linear approximation of just a one variable function, right, f of t. And we said that the essence of the derivative is essentially the fact that linear approximation works, right? So the essence of differentiability in multivariable calculus is that the tangent plane that I wrote up here, this plane that I wrote up here, that should work as an approximation for my function, for my two variable function, all right? So in one variable calculus, again, f of t, this is a right there at the point a, is approximately f prime at a, x minus a plus f of a, right? Again, with all the caveats of you have to be close by and all that business. So for f of x comma y to be differentiable, this has to be true. So this is approximately the formula up there where we throw z to the other side. Okay, so let's see. If I throw, or maybe let's throw everything but z to the other side, then we're going to get df dx times x minus a. And again, this is at ab times x minus a plus df dy at ab times y minus b, and then plus f of ab. All right. So again, it looks kind of terrible, but this is a number, constant. This is a number, that's a constant. And so this function on the right, this expression on, and this is a constant, f of ab is a constant. So this thing on the right-hand side is actually super, super simple because the only kind of variables are x and y. Okay, so what does it mean to be differentiable? So f of xy is called differentiable if this approximation that I wrote down, right, that's why I used the squiggly lines up there, works. And let me put that in quotes. All right, and by works, I mean it works in the same way that the approximation in one variable calculus works, where if you're close to a, then f of t is indeed roughly this right-hand side. Sorry, I guess this shouldn't be x minus a, this should be t minus a. Okay, so in other words, f of x comma y is roughly this business on the right-hand side. All right, if that's always true, or let me say it like this, if that's true at a comma b, then we say f of x is differentiable at a comma b. All right. Maybe I put that little, at a comma b, just to emphasize all of this is going on at a specific point at a comma b. Okay. And to be just differentiable, period, like everywhere, then you have to be differentiable at every single point. Okay. All right. So why did we go through all that? Well, the idea is that if this is true, if f is differentiable, in other words, if f really is approximately this right-hand side, then everything about the derivative of f, anything you want to know about the change of f, you can instead replace f with the quantity on the right-hand side. All right, and we very much want to do that because, again, the quantity on the right-hand side is super simple. It's just a x and a y, and then multiplications and additions. Okay, so f can be horribly complicated with square roots, logs, exponentials, sines, and cosines, but this right-hand side, no matter what, is just a constant times x minus a constant, right? Constant y minus a constant plus a constant. So it's ridiculously simple. And again, if you're differentiable, then any question about the derivative of f can be answered by looking at the right-hand side. All right. Okay, maybe I should write that out kind of like this. If I make up a new function, L of x comma y equals to that right-hand side, df dx at ab, x minus a, plus df dy at ab, y minus b, plus f of ab, right? I'm calling it L because L for linear, right? Then any question about change in f can be, or I guess little f, can be answered by looking instead at L. All right. And again, this is, again, with the caveats, change in f at AB, right? At AB. Because notice that if I look at different points, A comma B, the formula for my right-hand side is going to be different, right? Because this is df dx at AB, df dy at AB, f at AB. So if I'm looking at 1 comma 2 versus 3 comma 4, the right-hand side formulas will be very different. Okay, so even if I want to be kind of the most careful mathematically, I should actually even put L and then notate that this L only works at AB. So maybe L sub AB or something like that, right? L sub AB. Okay, if I want to be really kind of OCD about it, or not even OCD, but very careful about it mathematically. Okay. So before we go on, again, most functions that we're going to be playing with, all the functions that we're going to be playing with are going to be differentiable. All right. So they're going to have tangent planes. But again, you can easily make up functions that are not differentiable, where this approximation, where the approximation f of x comma y, is roughly L sub AB at xy, where this actually fails. Okay. But again, we're not gonna play with those functions in this class. Okay, why did we do all this? We did it because originally we wanted to answer the question of if we're at a comma b, how does my function change in directions other than the x direction and the y direction, right? How does my function change if I move in that direction, right? How does my function change if I move in this direction? So at this point, we're going to be able to answer that because, again, as long as our function is differentiable, then any question about the derivatives of f, in other words, right, how does the function change is a question about the derivative, right? So any question about the change in f, any question about the derivatives of f, we can just port to a question about L, all right? And L is so simple that things work excellently there, right? So let's actually see this. So one thing we can do, so this is moving into 15.4, is that actually we've got an hour here. Let me actually stop here. So this is next lecture, just so that these aren't too long. All right. So you'll have to stay tuned. I guess the cliffhanger here is, change in F is roughly the change in L. How do we use that to figure out the change in different directions? And that will lead us to the chain rule. That'll lead us to directional derivatives, and ultimately the gradient, which is 15.5.